Okay guys, in this video we are going to be talking about chemical equilibrium, and we'll also dig into this section on equilibrium constants as well. So for this first section I'm going to define or describe what equilibrium states are in chemistry, and then we'll talk specifically about the dynamic nature of chemical equilibrium. So an equilibrium state is a state of the system, a state of your chemical reaction mixture, where the forward reaction rate equals the reverse reaction rate. Okay? So for a reversible reaction, equilibrium is reached when the rate that you go from reactants to products is counterbalanced by the rate at which you go from products to reactants. Because the forward and backward rate are the same, there's no net change in the amount of reactants or products that you have. So you might start off a reaction with all reactants. That's very common. Over time, the forward reaction will occur with a higher rate than the reverse reaction. But as that forward reaction continues, its rate slows down and the backwards rate speeds up until they become the same. And when those two rates are the same, then there'll be no net change in the amount of reactants or products that you have. Now, that doesn't mean that microscopically the forward and reverse reactions are not occurring. In fact, they are occurring. It's what we call a dynamic equilibrium, in the sense that microscopically both the forward and the reaction rate continue, but because there's no net change in the composition, we say that the system is at equilibrium. So that term dynamic equilibrium refers to the fact that things are still going on microscopically, there's just no observable change at the macroscopic level. As we go throughout this chapter, we're going to talk about how the equilibrium composition, and by that I mean the relative amounts of reactants and products at equilibrium, how that equilibrium composition depends upon the concentrations of the reactants and products that you start with, the temperature of the reaction, as well as the pressure for a gaseous reaction, which is related to the volume of the reaction vessel for a gaseous reaction. So we'll get to, in the section on Le Chatelier's principle, we'll talk about these in detail. For now, I just wanted to show you a couple of graphical analyses of equilibrium. So here we're talking about a decomposition reaction. We've got dinitrogen tetroxide is decomposing into nitrogen dioxide. Initially, let's suppose that we've got all dinitrogen tetroxide. At some point, we reach, we're a little bit before equilibrium here, and so we're forming some of the product, the nitrogen dioxide, and that has a brownish color to it, reddish brown color to it. So you can see that the reaction vessel goes from clear when you have the dinitrogen tetroxide to a little bit, sort of tan, and then as you go further towards once you reach equilibrium, you see that you've built up quite a bit of the NO2. Here's what's going on in terms of the chemical concentrations. So if you were to plot the concentration of each gas as a function of time, you start off with some concentration of N2O4. The concentration of the product is initially 0 in this case. As the reaction proceeds, the concentration of the reactant decreases and the concentration of the product increases. Note the stoichiometry here, a 1:2 ratio. So what you see here is that the amount of NO2 that's formed is going to be larger than the amount of N2O4 that's consumed. And so we see that very clearly just due to the position of this curve above that one. But notice what happens after a certain time. We see that the concentration of the N2O4 stops changing, as does the concentration of the NO2. And it's this region here where the concentrations are no longer changing that we say that we have reached equilibrium. Let's also look at what happens in terms of the reaction rates, both the forward reaction rate and the backward reaction rate. So assuming that these are elementary steps in each direction, The forward rate is going to be some forward rate constant times the concentration of N2O4. The reverse rate is going to be bimolecular. It's going to be the reverse rate constant times the NO2 concentration squared. And so you can see that at the beginning, because there's a large concentration of N2O4, the rate of the forward direction is fast. It's a high rate. And because there's no product yet, the rate of the reverse reaction is, of course, 0. But as you start forming product and the reactant concentration starts decreasing, you see that the rate for the forward reaction starts to decrease, and the rate for the reverse reaction starts to increase because now you have some product being formed. At a certain point, the two rates equal one another, and then after that they stop changing. The rates become constant. And that's when we've reached equilibrium. So when the forward rate equals the backward rate, we've reached the equilibrium for the chemical reaction. Well, this next section discusses a very important quantity in chemical equilibrium called the equilibrium constant. We're going to be working with something also called the reaction quotient. I'm going to show you how to define those for any stoichiometric reaction, and then we'll have a few calculations to do along the way as well. So the equilibrium constant, the definition of the equilibrium constant is also called the law of mass action. Equilibrium constants, the reason we call them equilibrium constants is that they do not depend upon the initial concentrations of the reactants and the products. Okay, so it doesn't matter what you start with, the equilibrium constant for a reaction has a fixed value. It does depend upon temperature, as you can see at the bottom, but it doesn't depend on concentration, so that's why we call it the equilibrium constant. So here I've just set up a generic stoichiometric reaction that's reversible, and we'll suppose that the equilibrium concentrations, so once this reaction reaches equilibrium, the equilibrium concentrations have particular values. Okay, so whatever you start with, you'll wind up with some equilibrium concentrations of both reactants and products. The definition, I should say this is the shorthand definition of the equilibrium constant, is given here. You notice how we would calculate it. We would take the equilibrium concentrations of the products raised to their stoichiometric powers, or to their raised to the power of their stoichiometric coefficients. Okay, so this little c here is the stoichiometric coefficient from the reaction. Same thing with this little d. So it's the products divided by the reactants raised to their stoichiometric coefficients. I'm going to go ahead and write down the full definition of the equilibrium constant. Recall that these brackets represent molarity. That notation we introduced in the last chapter, but we just wanted to remind you that's what it is. So these brackets, they have units of moles per liter. And the equilibrium constant itself is a unitless quantity, and the reason why it doesn't look unitless in this formula that I have on the screen is because this is a shorthand for the equilibrium constant. So let me for this reaction, let me write out the full version. So Kc, the equilibrium constant expressed in terms of units of, or expressed in molar concentrations, has the following definition. You would take the equilibrium concentration of your product, and then you would divide it by the standard concentration raised to the c power, where c is the stoichiometric coefficient. It's a little confusing because there's so many c's here. Anyway, maybe having the d's will clarify it. So d equilibrium concentration divided by this standard concentration raised to the stoichiometric coefficient. And then you do the same thing in the denominator for the reactants. So this would be C naught raised to the little a Now C naught, the reason it's not put in this formula on the screen is because C naught is defined as 1 mole per liter. Okay, so what the C naught does is it really takes care of the units, right? The brackets here, this equilibrium concentration of species C is expressed in moles per liter, and then you're dividing by 1 moles per liter. So that gets rid of the units. Now, it's a lot of extra work to include all of these C naughts in the denominator, so we usually don't do that. In fact, we usually don't even put in the EQ. So the very shorthand way of writing Kc would just be concentrations raised to stoichiometric coefficients. And you just need to know that the equilibrium constant is only evaluated using equilibrium concentrations, and the equilibrium constant is always unitless. Okay, so those are some important features about the equilibrium constant. It looks like it depends upon concentrations, but it turns out that it doesn't, and that's what the law of mass action is all about. Even though, as we'll see in some of the figures that we go through, even though the equilibrium concentrations here, they depend upon the initial concentrations that you start with. So the amount of species C and D, A and B that you have in equilibrium, it depends upon the concentrations that you start the reaction with. Nevertheless, the equilibrium constant will always be the same. It's kind of strange, and so but that's what the law of mass action tells us. And so, regardless of what the equilibrium concentrations are, they are connected through stoichiometry in such a way that you always will get the same value of Kc at a given temperature, no matter what the initial conditions of the reaction were. The value of the equilibrium constant carries meaning. So this slide is very important. So this is our qualitative interpretation of the equilibrium constant. So the magnitude of Kc, how big or how small it is, indicates whether or not the reactants or products will be the dominant species at equilibrium. So here we've got our generic reaction and the equilibrium constant. If the value of Kc is very large, so much larger than 1, well, that means that the numerator here is going to be very big compared to the denominator. Okay. And what that indicates is that the concentrations of the products will be very large compared to the concentrations of the reactants at equilibrium. So when you see a very large Kc value, it indicates that the products are preferred at equilibrium. The reaction mixture at equilibrium will be mostly products. Conversely, if you find that the equilibrium constant is much, much smaller than 1, that means that the concentrations of the reactants will be large relative to those of the products at equilibrium. And so for this reaction here, a very small value of Kc suggests that at equilibrium you're going to have mostly reactants. If you have a moderate value of Kc that's on the order of 1, what you'll find is that at equilibrium neither the reactants nor the products will be favored. You're going to have a mixture of both, where both are present in significant quantities relative to one another. Okay, so a big equilibrium constant means mostly products. A small fraction for the equilibrium constant means mostly reactants. A moderate value means a good equilibrium of both reactants and products. Okay, so this is a very important aspect of the equilibrium constant. Let's see, what are we asked to do here? So we're given the Kc for this reaction. Does the equilibrium mixture contain predominantly reactants or products? Well, 4 times 10 to the 13, that is a large value. That indicates that we're going to have mostly products at equilibrium. Here we've got a follow-up problem. If the concentration of nitrogen monoxide equals the concentration of O2, which equals that value at equilibrium, what is the concentration of the NO2 at equilibrium? And so this problem is going to highlight that you can use the equilibrium constant to solve problems. So what I'm going to do is I'm going to write out the equilibrium constant expression for this reaction. So it's products over reactants. NO2 is our only product. And we raise each species to the stoichiometric coefficient. So we've got NO2, we'll raise that to the second power because of this factor of 2 in the reaction. Products go over the reactants. So NO, it'll be squared, and then we'll have O2, like so. Now, in this problem, they've given us these two concentrations. They've given us Kc. They want us to solve for the NO2 concentration. So after a little bit of algebra, we'll arrive at this expression. And we can plug in those numbers. So I'll go ahead and do that explicitly. Just to show you where everything is coming from. That will be the 1/2 power, taking into account the square root. So running these through our calculator, as long as I didn't make a mistake. Oops, looks like I did make a mistake. There we go. And so I'm getting 0.01, call it 8 moles per liter. Now, you're accustomed to problems where the units make a lot of sense, right? Where you keep track of all of the units explicitly. It's good to keep doing that, but it's a little difficult when you're working with equilibrium constant expressions because Kc is unitless, and we've also used this, as I said, this shorthand where we've gotten rid of the C0. And so a lot of times the units seem almost magical in equilibrium problems. Nevertheless, if you're using the equilibrium constant, if you've got the correct equilibrium constant expression and you rearrange it to solve for a concentration, the value of the units for that concentration will be moles per liter. Okay. This is just a connection that I'm making between this new material that we're talking about and the chemical kinetics that we talked about previously. So here is the chemical equation that we were looking at before. Where we had the graphics where we showed the equilibrium reaction. So this is the decomposition of dinitrogen tetroxide to nitrogen dioxide. We've got a forward rate constant and a backward rate constant. At equilibrium, the forward rate equals the reverse rate. Okay? And what we can do is we can use this equation to construct the equilibrium constant. Right? So from the new definition of the law of mass action, Kc is going to be the product concentration squared divided by the reactant concentration in this case. So just from the reversible reaction. And then if you take this equation and solve for this ratio, you'll find that the equilibrium constant is numerically equal to a ratio of rate constants. And so that's a common theme when working with the kinetics of reversible reactions. The equilibrium constants are always a ratio of the forward rate constant divided by the reverse rate constant. So there's our connection to chemical kinetics. And as I was saying, right, previously, the magnitude of Kc tells you something about which is going to dominate the reaction mixture at equilibrium. But if the forward rate constant is very large, Kc is going to be very big, and so you're going to have mostly products at equilibrium. Conversely, if the reverse rate constant is very large, that's going to make Kc have a very small value, and so you're going to have mostly reactants at equilibrium. Okay, and so you can kind of see that relationship here in this definition of the equilibrium constant in terms of rate constants. Because the rate constants don't depend upon concentrations, neither does the equilibrium constant. Because rate constants do depend on temperature, as we've seen through the Arrhenius equation, the equilibrium constant will depend on temperature. Okay, we'll talk about the temperature dependence, I think later on in the course, actually. We'll do some qualitative temperature dependence in this chapter in the next video, I think, but the quantitative calculations won't come until later, I believe. A related quantity. Okay, so a quantity called the reaction quotient. It's very similar to the equilibrium constant. The difference is that you can calculate the reaction quotient at any point in the reaction. You can calculate the reaction quotient at the beginning, halfway through the reaction, at the end of the reaction. It doesn't matter. You can always calculate a reaction quotient. However, the equilibrium constant is only calculated with equilibrium concentrations. Okay, so that's the difference between the two. And so I've tried to articulate that here in these two equations, where I've highlighted the equilibrium concentrations are used for Kc, but you might use initial concentrations for the reaction quotient. And there's a relationship between Q and K. When Q is greater than K, so if you calculate for your initial concentrations, if you calculate Q and compare it to the K value for the reaction, it indicates that the reaction needs to go back towards the reactants to reach equilibrium. The way I like to think about that is if K is bigger, if Q is larger than K, it's like the numerator here is too big for you to be at equilibrium. And so in order to get back to equilibrium, you need to make the numerator smaller and the denominator a little bigger. That is, you need to go from products to reactants to get back to equilibrium. Conversely, if Q is less than Kc, that's like having the denominator be too large to be at equilibrium. So in order to get back to equilibrium, we need to decrease the amount of reactants and increase the amount of products to take us back to equilibrium. The third possibility, of course, is what if Q numerically equals K? Well, that tells you that you're already at equilibrium. Let me show you a visual device that I use to help students remember this rule. So what I do, it's going to be a little picture that's easily memorizable. You put the equilibrium constant in the center, and you want to compare Q to K. Now there's two possibilities. Either Q is less than K or Q is greater than K. So I'm going to put those two possibilities on the board, and we're going to sort them. So one possibility is that Q is less than K, so I've drawn it to the left. Q is less than K, so I put it over here. The other possibility, Q might be greater than K, and so I'll put it on the right. Okay, now you want to get back to equilibrium. So go towards the equilibrium constant. Okay, so this is the complete diagram. It encapsulates the two possibilities. If Q is less than K, so I've written it on the left, I need to go to the right. I need to go to the products to reach equilibrium. Conversely, if Q is larger than K, so I've written Q over here, in order to get back to equilibrium, I have to go to the left. That would be to the reactant side of the reaction. Okay, so you can use this trick to help you remember these rules if you like using these types of things. So here's a set of diagrams that further illustrates the relationship between the equilibrium constant and the reaction quotient. So let me think of what the reaction is. I'll have to write that down here. Let's see. So this is the reaction of SO2 and O2 forming SO3, and certainly I've got to, let's see, what would I need to do here? Divide that by 1/2, so it should be 2, 2. That should be the balanced reaction. 4, 5, 6, 6. Yeah. So this is the gaseous reaction that these diagrams are illustrating. And so for the two panels on the left, okay, so for the left-hand side, notice that we start off with, it looks like 2 moles of, 2 moles per liter of SO2 and 1 mole per liter of oxygen. So they're being combined in the stoichiometric amounts. And then initially we've got no product. Okay, so what happens? The reactants start to react. Their concentrations decrease. While that occurs, the product concentration increases. Eventually, equilibrium is reached, and so these are the equilibrium concentrations. What's being plotted down here is the reaction quotient, Q, as a function of time. So in this case, Q would be the concentration of the SO3 squared over the concentration of the SO2 squared times the concentration of the O2. Now initially, at time t equals 0, the concentration of the SO3 is 0. So Q equals 0 initially for this reaction. Gradually, the amount of products increases and the amount of reactants decrease. So Q starts to get larger. It goes up. Once equilibrium is reached, the concentrations no longer change. Q becomes Kc at equilibrium. So eventually Q converges to K, and that's the value of K for this reaction. Here we've started in the second half here, the second half of the diagram, we've started with the opposite conditions. We've started with what appears to be, I don't know, let's call it, 2 moles of the product, but no reactants. Okay, so we're starting our initial conditions with all products and no reactants. What happens when you try to calculate Q there? Well, in that case, the denominator is 0, so Q equals 1 over 0. That's undefined. We see that Q has a very large, indeterminate value. It's infinity, essentially. What happens as the reaction proceeds? Well, you see that some of the product decomposes and the reactants build up. Eventually, you reach equilibrium. What happens to the value of Q in that case? Well, as the product starts to decrease in concentration and the reactant starts to increase in concentration, the value of Q comes down and it converges to K at equilibrium coming from the other end. Okay, so this slide was just meant to highlight the relationship between Q and K. Q changes during a reaction. However, the value of K is fixed as long as temperature is constant. This highlights another important aspect of equilibrium. This slide is meant to illustrate that the equilibrium composition depends upon the starting concentrations of your reactants and products. Okay, so we're considering this equilibrium reaction here, carbon monoxide reacting with water vapor to produce CO2 and hydrogen gas. It has a fixed equilibrium constant at a given temperature of 0.64. And what we have over here, we have three reaction mixtures. Okay, so this will be 3 experiments. In the first reaction mixture, we have equal concentrations of carbon monoxide and water. Okay, so we've got equal concentrations of the reactants. In this second experiment, we're going to start with equal amounts of the products. Okay. And then in this third experiment, we're going to have mostly reactants, but we're going to have a little bit of products in there as well with these values. Okay, so these 3 different reaction mixtures, at their initial time, they all have different values of Q. For the first mixture, Q equals 0. For the second one, Q is infinity. Here, because the products have a finite concentration, Q does take on a numerical value. It's not indeterminate like it was in this case. So what happens as these reactions reach equilibrium? You're going to get new concentrations for all of the reactants and products. So these are the concentrations you get for mixture 1, for mixture 2, for mixture 3. You have some amount of reactants and products in each case. Well, what happens when you calculate the value of Q from these concentrations at equilibrium? For each case, you get the same value, 0.64. You get the equilibrium constant. So even though the concentrations at equilibrium are different, this is what I call the equilibrium composition. What is the breakdown of concentrations for each species in the reaction? Even though the equilibrium composition is different for each of the mixtures, the law of mass action still holds. Furthermore, the concentrations you get at equilibrium depend upon the concentrations that you start with. So the composition at equilibrium depends upon the initial conditions. However, the equilibrium constant does not. Okay? And so that's what I wanted to show you on this slide. As we proceed in this chapter, we're going to learn how to calculate equilibrium concentrations from the equilibrium constant using a little bit of math and a tool called an ICE table. First, we need to know how to write up the equilibrium constant expressions. So that's what's going on in these in this problem. We want to write out expressions for, I guess they want us to write Q. So we'll write for part A, Q, C will be equal to the concentration of the ozone squared divided by the concentration of the oxygen cubed. Okay, it's products over reactants. Each species is raised to their stoichiometric coefficient. For part B, we've got ammonia as a product. That'll be squared divided by nitrogen, hydrogen squared, like that. For part C, we will have nitrogen dioxide to the 4th power, water vapor concentration to the 6th power, divided by the ammonia concentration to the 4th, and the oxygen concentration to the 7th. So that's our reaction quotient expression there. Now the next problem, so you need to be able to do this for any stoichiometric reversible reaction. You need to be able to write out the expression for Q, which is similar to the expression for K. You need to be able to do that for any stoichiometric reaction. Here's some for you to practice with. So go ahead and practice those when you have a chance. I'll leave them as an exercise for you. Let's have a look at this problem. See what they want us to do here. So we're talking about gaseous dinitrogen oxide, which is reforming the dinitrogen tetroxide. So this is the reverse of the reaction that we were playing around with earlier. It says that when 0.1 moles of NO2 is added to a 1 liter flask at 25 degrees Celsius, the concentration changes so that at equilibrium, the NO2 concentration equals 0.016 and the dinitrogen tetroxide equals 0.042 molar. First, they want us to calculate the reaction quotient. That's pretty easy. You may, in fact, this is, well, let me distinguish what they want. They want us to use the initial concentrations to calculate the reaction quotient. The amount of product initially is, it's assumed to be 0. They've implied that there is no product initially. So for this expression here, this would be the reaction quotient expression. You'd be plugging in 0 in the numerator, and you'd plug in 0.1 molar squared in the denominator. Well, that's still going to give you 0. So initially, the reaction quotient is 0 when there's no product. Then they want us to calculate the equilibrium constant using the equilibrium concentrations. Okay, so there we would take the N2O4, and I'm going to just be explicit. You don't usually have to put this in there as long as you know what you're doing. I'm going to put it in just to let us know that we need to be using the equilibrium concentrations. And just to make it match, I'm going to put an I up above to let us know that those were the initial concentrations. Okay. So we've got 0.042 for the product. Divide that by 0.016 and square it. for the reactant. Run that through your calculator. And I'm getting 164. Nothing wrong with that value. They can be equilibrium constants can be that. That's not a terribly large equilibrium constant. They can be much larger than that. They can also be very small. They're always positive, and they are unitless. So that's the number I'm getting. Let's see here. For this problem, for the reaction involving SO2 to produce SO3, they give us the equilibrium concentrations, calculate the value of Q. So this isn't a terribly difficult problem either. You need to write out the expression for Kc. That's what they want. SO3, we'd square that. SO2 squared, O2, products over reactants. And then they give us all the numbers that we need to fill in. So it'll be 1.1 in the numerator squared over 0.092, that's squared. And then the O2, 0.35. Run that through your calculator, and that's the equilibrium constant. And if I've entered the numbers incorrectly, I'm getting 408. Okay, so you want to be able to take the equilibrium concentrations and calculate the equilibrium constant. So that's one type of problem that we need to be able to do. Let's see. Is this one worth doing? Yes, this is a good one to do. Okay. So here, I'll just do one of them and then I'll let you do the other ones. So this is a problem where they give us the equilibrium constant and they give us initial conditions for the reaction mixture. And they want you to predict which direction does the reaction need to go to reach equilibrium. So this type of problem, they want you to calculate Q, the reaction quotient, and then compare it to K. And I've shown you this visual trick that you can use when you compare Q to K. Q is either going to be smaller or greater than K. And this little device shows you which way you need to go to reach equilibrium. So let's calculate Q for experiment 1, and I'll let you guys do the other ones. So you want to write out your expression. So we'll take the concentration for CO2 times the concentration for H2. Divide that by the carbon monoxide concentration, initial one, and the water vapor's concentration initially. Okay, so this left column here, these are the initial concentrations. And so we're going to wind up with 0.004 times 0.004 in the numerator divided by 0.0203 times 0.0203 in the denominator. We'll call it 88. What situation are we in? We're in the situation where Q is less than K. So in order to get back to equilibrium, the reaction needs to go to the right. So in order to get to equilibrium, this reaction is going to produce more products and it's going to consume some of the reactants. These problems, as well as these extra experiments that I didn't do, you would do the same thing for experiment 2 and for experiment 3. And then for all of these problems, it's the same thing. They give you initial conditions. You need to calculate Q and compare it to the given value of K using this device. Or if you just memorize the rules, you can use that as well. There are a couple of tricks here, though, and let me just talk about what those tricks are. In part A, there's no trick really at all. They're giving you moles of each species initially, so they give you the initial number of moles, and then it's a 1 liter flask, so numerically the value of moles divided by 1 liter is just equal to the molarity. And so then you plug those molarities into the reaction quotient expression. Now, for the next problem, it's a little different. Notice they've given you a 5 liter flask, and they've given you masses of each of the gases. So you need to put molarities into your reaction quotient expression. So you need to convert these grams, these masses, to moles using the molar mass of each species. And then you need to divide by 5 liters because that's the volume. Okay, so convert to moles, then divide by the volume to give you the molarity of each species. So you've got to do a little bit of extra work at the beginning to get the initial concentrations, but then from there you just plug them into the reaction quotient expression. The same thing here, only in this case there's no products listed, so you can assume that the amount of products initially is 0. That means the reaction quotient is also 0. So in order for this reaction to get to equilibrium, you're going to make some products. So this reaction is definitely going to go to the right, towards the products. Okay, so you want to practice these. I call these the QK comparison problems. And we'll see problems like this throughout the course. So we're going to do this not only in this chapter, we're going to do this type of thing in the next one, and the one after that, etc. Let's talk a little bit about gaseous reactions. Okay. So for gaseous reactions, it can be very convenient to work with partial pressures as your concentration unit. And so instead of defining a Kc in terms of molarity, you can talk about a Kp in terms of partial pressures. And so the way that you, and it's constructed in the same way, it's just instead of using molarities, you use partial pressures. So for this gaseous reaction, your Kp expression, that's the equilibrium constant expressed in terms of pressures, would be the pressure of methane here times the pressure of the water vapor divided by the pressure of the carbon monoxide divided by the partial pressure of the H2 cubed because of that stoichiometric coefficient here. Now Kp is also unitless, just like Kc. Let me show you for this reaction the full expression. It would be the partial pressure of methane divided by a P naught, P0. This would be the standard pressure. You do the same thing over here for the water vapor. For our purposes, we will simply take P0 to be 1 atmosphere. Now, usually it's actually taken to be 1 bar, which is another type of pressure unit. It's very close to an atmosphere. They're almost the same, but they're not quite the same. The true standard pressure is 1 bar, but for our purposes, we'll just take that to be 1 atmosphere. Now, numerically, Kp and Kc are not necessarily the same thing. They don't have the same numerical value, but you can convert one to the other using this formula that's given down here. And this formula is based upon the ideal gas law. So notice here's the ideal gas law. P partial pressure equals number of moles of a component divided by the volume times RT. Well, number of moles of gas divided by the volume is just the molarity of the gas. So if you take this expression for the partial pressure of gas I and plug it into all of these different places here, you can rearrange the expression in terms of the equilibrium constant for the molarities times this factor RT delta N, where delta N is the change in the number of moles of gas. Okay, so I'm going to write that down. Delta N is the change in the number of moles of gas. So for this reaction that we have on the board, delta N will be equal to, there's 2 moles of gas in the products minus 1 plus 3, 4 moles of gas in the reactants. So it's products minus reactants. In this case, we get minus 2. And so the expression between Kp and Kc is that Kp will be equal to Kc times RT to the minus 2. And if you like, you can write that as Kc over RT squared. So you can numerically convert a Kc value to Kp and vice versa. It can go either way. In this expression, you should use R equal to 0.0821 liter atmospheres mole Kelvin. Okay, so that should be the value of R that you use based upon my definition here. Okay. So this problem, they want us to practice writing out the Kp to Kc expressions. Okay, so I'm gonna write the general formula times RT to the delta N. So for part A, we need to calculate delta N. Delta N is going to be 2 moles of gas in the products minus 1 mole of gas in the reactants. So Kp is going to be equal to Kc times RT. For part B, delta N, I see 2 minus 2 in the reactants gives you 0. In this case, Kp is numerically equal to Kc because there's no change in the number of moles of gas. I should have put a little G in here, so parentheses G. I left off the phase subscript, the phase indicator for the water. Let's assume it's water vapor, so that it's 2 minus 2 gives us 0. For part C, we've got delta N is going to be 2 moles of gas in the products minus a total of 4 moles of gas in the reactants. So minus 2 again. Kp equals Kc. That'll be over RT squared. For part D, let's go ahead and say that delta N is going to be, I'm getting 3 minus 5 equals minus 2 again. So our Kp is going to be equal to Kc over RT squared. They give us Kc and they give us the temperature. So it's going to be 0.28 in the numerator divided by 0.0821. We really don't need the units. We do need to convert 900 degrees Celsius to 273 though. 1173, and then those are both squared. So 0.28 divided by 0.0821 squared divided by 1173 squared gives us a value 3.0 times 10 to the minus 5. And again, Kp is unitless. Okay, so here's a whole nother set for you to practice with. So you want to attempt these. Be sure you can generate the relationship between Kp and Kc, and if needed, to actually do the conversions. And you should be prepared to go both directions. So you might be given Kp and need to calculate Kc. All right. Well, this slide describes another rule that we use for equilibrium constants. If you have looked carefully back through all of the reactions that we've done so far in this video, you would have seen that they were all gaseous reactions. Maybe there was an aqueous reaction, but you wouldn't have seen any solids or pure liquids. Okay, and so there's a special rule for solids and liquids that I wanted to tell you about right now. And so what we're talking about is the difference between homogeneous equilibrium and heterogeneous equilibrium. In homogeneous equilibrium, all the species have the same phase, so they're all gases in the reaction, or they're all aqueous. That's very common, and we'll be doing a lot of problems involving that. But there's also heterogeneous equilibrium, where some of the reactants and products have different phases. Well, when you spot pure liquids and pure solids in your chemical reaction, you need to employ the rule down here at the bottom. That is that pure solids and pure liquids are not included in the equilibrium constant expression because they effectively have a constant concentration. The way I like to think about it is if you increase the number of moles of a solid or a liquid inside a reaction mixture, not only do you increase the number of moles, but you also increase the volume of that sample, of that solid and that liquid. And so as a consequence of that, the molarity, the concentration, doesn't change. In a nutshell, that's the physical intuition why we don't include solids and liquids in the equilibrium constant expressions. And so let's practice some heterogeneous equilibria. So for part A here, notice that we've got a solid on the left and aqueous ions on the right. So this is the dissolution reaction, and the equilibrium constant for this guy is going to be simply the concentration of the ions raised to their stoichiometric coefficients, but you don't include the solid lead because it's a pure solid, okay? So you leave out the pure solids. For part B, I'm going to go ahead and write this one as a Kc. You notice that we've got a solid product, we've got a solid reactant and a gaseous product, so it's going to be just 1 over the concentration of the CO2. It might also be reasonable to simply express this as a Kp using 1 over the partial pressure of the CO2. For part C, why don't we go ahead and do a Kp, since most of the active ingredients here are going to be gases. So we'll have the partial pressure of CS2 over the partial pressure of the monoatomic sulfur squared. And we leave off the solid carbon. Now the carbon is active. I didn't mean to say that it was an inactive ingredient, but we don't include it in the equilibrium constant expression because the carbon has a constant composition or constant concentration. So as long as there's some carbon present, we'd be able to establish the equilibrium. For part D, this is a vaporization. And for fun, I'm just going to do this as a Kc. There's no reason. I could have done it as a Kp if I wanted to. I'm going to say that this is the concentration of the bromine. And because both species involve Br2, I'm going to write it as gas in here, just to distinguish it from the liquid. But I don't include pure liquids in my equilibrium constant expressions either. Okay, so you need to remember to leave those out. Let's see, I've got another idea that I wanted to present to you. Not that. Over the course of the semester, we're going to be manipulating chemical reactions and equilibrium constants. And so here I'm just laying some groundwork to show you how you do that kind of thing. Very commonly, you might need to add 2 reactions together, especially in thermodynamics. So here we've got 2 equilibrium reactions that might be taking place in the same reaction mixture. Okay, so competing reactions. What you can do is you can add these reactions together, and you'll notice that because methane here is a product of one reaction and a reactant on the other, that when you add these 2 reactions together, the methane cancels out. And I think that it's the only thing that cancels out, if I'm not mistaken. We do have a little bit of cancellation here from this hydrogen and that hydrogen, so hydrogen is ultimately a product, but the methane is the only species that cancels out. Let's suppose that this first reaction had an equilibrium constant K1, and this second reaction had an equilibrium constant K2. You can show that the equilibrium constant for the third reaction is equal to K1 times K2. And you can do this for yourself explicitly. How you would do that would be to write out the expression for K1 explicitly, write out the expression for K2 explicitly, and then multiply those two things together, and then compare it to the equilibrium constant for the third reaction. When you write it out explicitly, you're going to find that they're the same thing. Okay, so when you add reactions together, you multiply their equilibrium constants together. When you multiply a chemical equation by a stoichiometric coefficient, so what I've done here is I've doubled the stoichiometric coefficients. That has the effect of increasing the equilibrium constant by a similar power. So if you double the coefficients, you square the equilibrium constant. If you triple the stoichiometric coefficients, you would cube the equilibrium constant. Reversing a reaction, let's see, I don't know that I took this reaction here and I reversed it. That is, I exchanged the reactants and the products, flipped it around. That's equivalent to multiplying a reaction by -1. And so for the equilibrium constant, you would take the equilibrium constant K1, you would take it to the -1 power, so you end up taking a reciprocal of the equilibrium constant. Okay, so whenever you reverse a reaction, you take the reciprocal of its equilibrium constant. And we'll do that from time to time as well. Okay, so I just wanted to lay out these algebraic rules for manipulating chemical equations and their corresponding equilibrium constant. Well, I'm going to go ahead and stop this video here, and we'll pick up with Le Chatelier's principle in the next one.